Now it should be on. Yeah. So, hi everybody. I'm Alessandra. As Rosario said, I work in the Netherlands. I'm originally from Italy. I do a lot of research on late-time universe. Can you hear me? Yeah. And I'm heavily involved with Euclid, which is a mission that combining weak lensing and galaxy clustering will give us a lot of things, and in particular is addressing the question of what is sourcing acceleration, cosmic acceleration. For Euclid and for many other missions, we are facing the question of how to test our theory of gravity on the large scales that characterize the universe and that are characteristic for cosmic acceleration. We have tested general relativity very well on local scales around compact objects in the solar system, but then we extrapolate to, by orders, something like 15 orders of magnitudes in length scale, and we apply to the universe on the large scales. And there are some puzzling questions that we are confronted with, which make us thinking about the possibility of modifying somehow general relativity. So I'll focus on that, and I refer to that as going beyond the standard model of cosmology, in which cosmic acceleration is sourced by the cosmological constant. So for today, I'll give an overview of what we call the theoretical landscape or the gravitational landscape. If you go beyond lambda and try to find a different possibly different explanation for cosmic acceleration, or still you want to simply test whether general relativity is the correct theory of gravity for the large cosmological scales, I'll give an overview of all the things that are out there and possibilities and what has been explored, in particularly what has been explored over the past 2 decades since cosmic acceleration has been established. And that will be for today. Then tomorrow I'll focus on a popular and infamous theory of modified gravity, which is FOR. I spent most of my PhD working on FOR theories and their cosmological implications. And it took me some time to remove the FOR label from my head. Anyhow, so it is one of the simplest modifications behind Einstein's general relativity, and it turns out to be a very useful toy model. We can do a lot of things analytically, and we can gain a lot of insight into what happens with cosmology as soon as you go beyond the Einstein-Hilbert action. What happens to background expansion, but also FOR was key to learning some characteristic features of modified gravity at the level of perturbations. What do we expect to see in the growth structure? What do we expect to see for weak lensing? And it's one of the few models for which we have working and validated embodied simulations. And so it's also one of the few models that give us an insight into the nonlinear regime. After that, I will generalize. I go basically in the order in which things happen. Back in the, how long ago? 10 years ago, a bit more, when I was doing my PhD. FOR was the model, and we were all studying it and learning what happens cosmologically. And then from there, we generalized. We understood that those features that we were observing for FOR were quite peculiar of many modified gravity models. And so there was a sort of shift in the years towards what are known as model-independent approaches to cosmological test of gravity. So can we use cosmological observables to learn something about our theory of gravity, going from data to the theory, rather than popping up different candidate models and fitting them to the data? That's the idea behind model-independent approaches. So I describe all those approaches, and then one of these, which is particularly successful and recent, is the so-called effective field theory of dark energy. And I want to dedicate the full final lecture to that and show you how we can use it its application to cosmological tests of gravity. So, I mean, it's a school on observational cosmology, so I don't need to spend much time on this introductory slide. It's just to remind us all that observational cosmology has been extremely successful. And since when general relativity was established as a good theory for studying our universe, since Hubble observation of the velocity of receding galaxies, then there has been enormous progress, in particular in the last decades, observing many different things such as cosmic microwave background, the clustering, weak lensing, and so on. We have come to establish a standard model for cosmology. We know a lot about the universe, the different eras it went through, and we also know with quite some confidence, to the point that the Nobel Prize was given, that at some point, contrary to our expectation, the expansion of the universe starts speeding up. And that's for the last few billion years in the history of the universe. And we say that this era is somehow dominated by a dark energy, something that we have really no idea what it is. If we stick to general relativity and the standard model of cosmology, then what is sourcing this accelerated expansion is the cosmological constant. Dark energy is a general word to mean, you can mean also cosmological constant or any dynamical form or alternative theory of gravity that would explain this cosmic acceleration. If you interpret it, if you stick to general relativity, so interpret whatever sources cosmic acceleration as an additional source of your energy momentum tensor, then nowadays we need 68% of this additional thing to be out there. We need this additional thing to make up 68% of the energy budget of the universe right now. Of course, there's the other unknown, which is dark matter, and I assume we have solved that problem, so I'll focus on dark energy. As to say, I'll focus on dynamics of the universe at late times in the last few billion years. So what do we do in the standard model of cosmology? We introduce, as Einstein did originally and then discarded, a very innocent-looking constant here, which obeys the symmetries, is allowed. We can have it there. And turns out that if you introduce this cosmological constant in your action and you leave everything else as it is, the Einstein-Hilbert term here, so the Ricci scalar, and an action for matter, you can think of this as actually contributing a constant energy density to your energy momentum tensor, and to have a pressure which is equal to minus the energy density. That turns out to so the equation of state that characterizes this fluid would be exactly -1, W equal -1, which is smaller than -1/3. So it's such that you can source an accelerated expansion once this component starts dominating. So we might have the solution and be done. And lambda CDM is up to some tangents that we are experiencing right now, is quite a good fit to most of the data that we have out there. Still, we are left with some questions. What goes in here, and what do we measure it to be? So we measure it to be, so how do we measure it? From gravity, basically, from its gravitational effect. We look at the dynamics of the universe, and we infer how much energy density should be contributed by this constant, this cosmological constant. And we find a number, which is this, 10 to the -3 eV. Then we try, from the theoretical point of view, to understand what would be in there, besides a bare constant that we can put by hand, and we expect the vacuum energy of all fields from quantum field theory to contribute to this lambda term. And that makes it a bit embarrassing, because depending on where, at which point, at which energy scale you declare your ignorance about the completion of your theory, you have to sum the 0-point energy of all your oscillator, all your particles, up to that energy, and depending on whether you say, okay, we have actually tested our standard model up to more or less TV, who knows what happened afterwards, maybe supersymmetry kicks in and kills my vacuum energy or whatever, or maybe I declare ignorance up to the mass Planck scale, Planck mass scale. It doesn't look good either ways. You have a huge discrepancy between the observed value and the theoretically expected one. And that means that you would need to, if you can always introduce this bare cosmological constant by hand, but you will need to do an extremely fine-tuning of its value in order to cancel all the contribution that comes from the vacuum energy. So it's a bit uncomfortable. The other question that we are presented with is why, and this is in logarithmic scale to make it more dramatic, but why are we living in this special moment in which dark energy is exchanging with matter in the domination? We seem to live in a very special moment, which is here, when you go from matter domination to dark energy. So there are, to the cosmological constant problem, you might have heard the old and the new cosmological constant problem. And I want to make the point that it is not necessarily this vacuum. If you interpret your cosmological constant as coming from vacuum energy, it is not necessarily, it was a problem already before cosmic acceleration was observed, because you would expect a contribution from your vacuum energy, and you weren't observing it from looking at the dynamics of the universe. So that was the old cosmological constant problem. Why is that we do not observe the gravitational effect of vacuum energy? How is it that it is zero? Then we observe cosmic acceleration, so maybe we need indeed this vacuum energy. The problem is that we need a tiny value. So the new cosmological constant problem is, if I want to source cosmic acceleration with vacuum energy, then why is vacuum energy not zero, but still a tiny value? Many of the models I will be talking about are models that address the problem of cosmic acceleration, so try to explain the accelerated expansion with something that is alternative to the cosmological constant, but most of them forget about vacuum energy completely. So there are few of these options, and I will highlight those, that address the problem of cosmic acceleration and the gravitation of vacuum energy simultaneously. And those are known, for instance, as degravitation models. So where you degravitate the vacuum energy in such a way that its contribution is tiny to the point of corresponding to your cosmic acceleration. But many of the other models, quintessence and those other things, really focus on the dynamics of the universe and forget about vacuum energy. So that problem, most of the times, the elephant in the room is still there, okay? Just to say that this problem of the vacuum energy, cosmic acceleration, are often presented together and are often combined with the idea of modifying gravity on cosmological scales. I like to see them sometimes separate. I mean, we still have to test gravity with high precision on cosmological scales, like we did on the solar system. We still have the problem of the vacuum energy, and we still have cosmic acceleration to solve. The solution might wonderfully come in one theory that solves all, but it might be three different things, so just to stress that. Now, how special is general relativity? Why are we sticking to it? And there's a couple of theorems that tell us about how special general relativity is, and one is the so-called Weinberg-Desert theorem that tells you that it's basically the unique Lorentz invariant theory of a massless spin tube. So if you want to go beyond general relativity, basically at the end of the day, what you end up doing is changing the number of degrees of freedom of your theory, introducing new dynamical fields. Whether you do that by breaking explicitly your Lorentz invariance, whether you do that by going to higher dimensions or to give mass to a graviton, at the end of the day, especially from the point of view of cosmological test of gravity, what you see at that sort of lower energies relevant for cosmological perturbations, what you see is some new degrees of freedom. Whether you started from a 5-dimensional theory of gravity, a massive one, or simply quintessence, what we care at the end of the day, what we see, is new degrees of freedom. Another equivalent theorem, basically, is that of Lovelock. Lovelock, in the 1970s, formulated what is known as Lovelock's theory of gravity, where he said that basically the same thing, that GR is the unique theory that you can build if you stick to locality Lorentz invariance, and you have second-order equations of motion for your massless graviton. Lovelock went a bit beyond. He didn't stick to 4 dimensions. He also did a lot of interesting work in finding what could be the most general metric theory of gravity, so a theory of gravity where gravity is mediated by your, where you have a metric describing gravity, right, and focus on the graviton, the massless graviton. And he asked himself what would be the most generic action, Lagrangian, that you can write if you want your resulting theory in d dimensions to have second-order equations of motion. So he went through this exercise. It looks like a cumbersome expressions. Here is the sum over different combinations of your Riemann tensor. Now, the upper limit here depends on the dimensions in which you work. If you work in 4 dimensions, t is equal to 1. If you work in 5, t is equal to 2, and so on. This is a generalized Kronecker delta. I'll have at the next slides giving some expressions for it. And this is just the Riemann tensor, and there's a product in here. So he managed to identify in a generic number of dimensions what's the most general action that you can write in terms of geometric invariance, so that the resulting equation of motion for your graviton will be second order. Now, not surprisingly, in 4 dimensions, that happens to be a constant and a Ricci scalar. Gauss-Bonnet term starts to be relevant only if you go to 5 dimensions. In 4 dimensions, as you probably know, this would be a total derivative, boundary terms that you disregard. So this just if you want to know the expression of this generalized Kronecker delta. I don't think you will ever calculate these things, and you find that there's a whole Wikipedia page on Lovelock's theory of gravity. Another interesting thing is that basically by writing that Lagrangian, he identified geometrical invariants that are known as Lovelock scalars that have the property that if you write an action in terms of these scalars, or even nonlinear functions of these scalars, you will not introduce an extra tensorial degree of freedom. You might introduce new scalar degrees of freedom. And you have to be careful about whether those are ghost-like or not. But from the point of view of tensor, you will not introduce any new tensorial degree of freedom, so you are safe from Ostrogradski's instability for your tensor. You're not going to have a ghost degree of freedom there. And so that's the context in which you can think of f of r. F of r is a nonlinear function of r. You can also, people have played also with f of g, where the g is this Gauss-Bonnet term. Again, if you add any nonlinear function of this, you will not introduce any tensorial degree of freedom, but you will introduce a scalar in this case, a scalar in this other case. There is a peculiar case in which you can have a nonlinear function of both r and g and still manage to introduce only one extra degree of freedom. You're really just freeing up some of the degrees of freedom that were silent inside your metric because you're changing the constraint equations. That's what you're doing. And that's when you introduce a function that obeys this constraint. Now, that was Lovelock. 1971. Lovelock had a PhD student, Hordesky, in Waterloo, Canada. And there's a very interesting story about Hordesky. So I'm here standing by a painting. And this painting was made by Hordesky. And we have just purchased it in Leiden. So it's real art. It's the first time in my life that I own, not really myself personally, but a real painting from a painter, okay? So what happened? So Hordensky was a student of Lovelock, and I'll tell you later a bit more about his work. It was a generalization of Lovelock. So Lovelock basically worked out the most general action that you can have for your tensor if you want to stick to second-order equations of motion. And then Hordensky did the same thing, but if you want to have a tensor and a scalar degree of freedom, and still have second-order equations of motion. He was briefly a professor in Waterloo, but then he left the field. So a few years after he did this nice paper, he left the field, and he became a painter, a successful painter. He has exhibitions throughout the US. He lives in Santa Fe. He does a lot of Van Gogh-inspired paintings. And there's always some stars and stuff in his paintings. But anyhow, that's it. A few years ago, I think it was around 2011, Hordensky gravity becomes extremely popular in cosmology. We get to it through generalized Galileans that I will describe shortly after. So suddenly, if you check his original paper from 1974 now, it has more than 1,000 citations. So a PhD student from Heidelberg that was working on Hordensky gravity contacts him, asking if he can include one of his paintings in his thesis. And the guy is like, what? And so I was surprised, and he came back. He has published a few papers from them. And he told me he's working on 2 other papers right now. So it's a very interesting story. So basically, his theory stayed silent until he was rediscovered a couple of decades later. And then he thought of making a painting about this theory. So this is Hordensky's scalar theory. And that's the action in there. And it's really beautiful. OK. But I'll come back to that. So now, let's say we are stuck at Lovelock. We don't know what Hordensky did. And we wonder, so OK, that's what the most general theory for a second-order equation of motion for my tensor. I have basically general relativity in 4 dimensions. What can I do if I want to go beyond that? And I'll show you the next slide, with a crazy amount of models that people have tried to go beyond general relativity and the cosmological constant. But roughly speaking, it's not an exact analogy, but you can think of it as when back in the 19th century, there were discrepancies in the orbits of planets. And at one point, it was Leverrier that solved the problem by predicting the existence of a new planet that hadn't been seen yet, but was perturbing the orbit of the other in such a way to explain this discrepancy. And that was when Neptune was found exactly where Leverrier predicted it. And they fixed the orbit of Uranus that way. You can roughly think of that case as dark energy, as when you want to solve your problem of what is sourcing cosmic acceleration by introducing a new component that we haven't seen yet. But you can also go the other way and do what we needed for Mercury's orbit. Leverrier tried again for Mercury's orbit to predict a new planet, but it didn't work. At the time, you needed to go from Newtonian gravity to general relativity. So that's the rough distinction. It becomes very complicated, but that's the rough distinction between dark energy and modified gravity. Of course, we never do anything as revolutionary as going from Newtonian gravity to general relativity. But that's the rough idea. So let's see what people have done in these directions. We have the cosmological constant still there, very good model for all our observations. There's some back reactions models in which inhomogeneities are taken into account when looking at your expansion history and could explain the observations. They're not so successful. And then you can think of going Einstein way, modifying your theory of gravity, or Leverrier way. And then you keep going. In lambda, if you stick to lambda, there might be some landscape possibilities to explain the smallness of the observed value. But if you go on the 2 main branches, modified gravity and dynamical dark energy, then what can you do? Well, you can introduce a scalar field and dynamical. you can keep it minimally coupled or non-minimally coupled to gravity. If you go on the other side, as we've seen from those theorems, you can start breaking Lorentz invariance, giving mass to the graviton, or introducing what are known as scalar tensor theories. F of r will be in here, so you still keep your massless spin 2, but you vary the constraint equations of your theory in such a way that you free up more degrees of freedom in your metric. Now, you already probably know that some of this theory at the end of the day are really equivalent to what you would call a non-minimally coupled dark energy. So the distinction between what we call dark energy and modified gravity becomes not so clear anymore. Giving mass to the graviton, I will briefly discuss massive gravity models. I'll have just a slide about it. I'm not an expert of that. It's a very challenging effort. You can also, there's also models in which a second metric is introduced. Degravitation, I mentioned it, and I will talk a little bit about it. You can go to extra dimensions, of course. And typically, the tension of the branes becomes your scalar degree of freedom that you need at the low energies characteristic for the expansion of the universe to source cosmic acceleration. So let me talk a little bit about these models. Then for the next lectures, I will go more on the observational side and focus on their implications, signatures on large-scale structure, cosmic microwave background, etc. So F of r, there you go. F of r is this simple model in which you start from your Einstein-Hilbert action. You don't do anything to your matter sector, but you modify, you introduce this nonlinear function of r. It was first considered for inflation. In there, you have something like positive powers of r, and because you need a term that is important at high curvature, so at early times. And that's, for instance, Starobinsky model of inflation, which is still a good fit to the data. Then it was somehow revisited in the context of cosmic acceleration. So the game is simple. For inflation, I need some extra terms that are relevant at early times, so at high curvature. If I want to source cosmic acceleration, I want something that starts being important at late times when matter is diluted, and so something that is inversely proportional, roughly speaking, to my curvature, to the Ricci scalar. Okay, so if you introduce that, and that's a Lovelock scalar, we are sure that we will not introduce any new tensorial degree of freedom, but you see that you introduce, your equations become higher order. These are Einstein equations. If you vary, I'll go through some of the steps tomorrow, but if you vary this action with respect to the metric, these are the equations you end up with. Here with f sub r, I indicate the derivative of f with respect to r. So you do see that with respect to the standard Einstein equation, you have extra terms, and the tricky ones are here, because you have derivatives acting on f sub r. And f sub r, at the end of the day, it's a function of the metric. So you have higher derivatives acting on your metric. And so you can already expect that some of the equations that used to be constrained equation will not be that anymore, will be dynamical. And indeed, you can see that, I'll do the steps tomorrow, but let me mention that these terms comes from this bit of the action. When you vary it, you have such a term also in GR when you vary it, but typically it's a boundary term, and you neglect it. Now it comes multiplied by f sub r in our case, so you cannot really neglect it. You can use partial derivation to move the derivatives on f sub r, but it stays with you. And then another simple way to see and identify what this new degree of freedom is by looking at the trace equation. So if you take the trace of Einstein equations, you have in standard GR, what you have is that the Ricci scalar is equal to the trace of the energy momentum tensor. Now, if you take the trace of this equation, what you have is a D'Alembert entering here, acting on this f sub r. So it's very standard to identify the new degree of freedom as this scalar here, which also has been dubbed by Starobinsky as the scalaron. At the end of the day, f is a function of r, so it's a function of your metric. So what you're really doing is that you're making more of your metric degrees of freedom dynamical. But it's really nice to identify it with a scalar. So whenever you see anything about FOR theories, you will see a lot of constraints about values, for instance, of this f sub r today. And I'll also try to talk, if not today, tomorrow, about screening mechanisms that are something that is very important to make sure that when you go to, even if you vary your theory on large scales, when you go towards smaller and more dense regions where gravity has been tested very well, you reproduce general relativity. And screening mechanisms, we learned a lot about how they can work from looking at f of r and looking at the equation for this f sub r scalar. F of r is a subcase of Brans-Dicke theory, now generalized to GBD, generalized Brans-Dicke. So originally Brans-Dicke introduced in 1961 such an action that was based on the idea that maybe it would make more sense to have a Newton constant that depends on time. And so something that is not a constant really, but it's a varying constant. And they achieved that scenario by introducing a scalar field, non-minimally coupled to your metric, with such kinetic term and potential. That was the original Brans-Dicke, where omega is a constant. F of r is the subcase of this one with omega equals 0. Now, there's a more general version, modern version of Brans-Dicke, which is up here, where I have a general non-minimal coupling to r. And then I have a rescaling here, also more general function in terms of the in front of the kinetic term. Now, any theory written like this, what it does, it introduces this scalar degree of freedom, which is non-minimally coupled with the metric, and there's a consequence. Here I'm neglecting matter, but what the consequence of this non-minimal coupling is really that there will be a new fifth force between your matter particles. So that's the problem that we encounter when then we go to local test and we want to hide this fifth force. So this is just giving you the equations. So again, if you go through the exercise of varying with respect to the metric and varying with respect to the then the scalar degree of freedom, right? So you can write the Einstein equations in terms of an energy momentum tensor for your scalar field and terms that we have already encountered in f of r. Quintessence, I didn't mention quintessence. Maybe I should have started from there. It's one of the simplest things. The first things that people try when cosmic acceleration, in particular when cosmic acceleration was established, and it's just introducing a dynamical scalar field. So the idea behind having a dynamical scalar field was to try to address, in particular, the coincidence problem. So why the energy density associated to this cosmic acceleration is starting to exchange with matter right now. So people were looking for tracking solutions of your scalar degree of freedom. Quintessence, I mean something that is a subclass of GBD, but for which there's no minimal coupling. So it's a minimally coupled theory with a standard kinetic term. And then it's a very simple fluid. You can interpret it in terms of a fluid which has this equation of state. And you see easily that if it's slowly rolling, so if the kinetic term is negligible with respect to the potential term, then you achieve something, a W, which is very close to -1. So you sort of mimic the effects of a cosmological constant, but through a dynamical field that maybe give you an anchor to explain problems such as coincidence in a dynamical way, so in a technically natural, hopefully, way. Okay, so now let me jump from general Brans-Dicke to what are known as Galileans. So I'm still sticking to scalar degrees of freedom, adding a new scalar degree of freedom. So Galileans are now very popular models for cosmology or models for cosmic acceleration. They correspond to basically the most general action that you can write if you want to have your tensor, massless tensor, and one scalar degree of freedom, and your equations of motion to be second order at most. And I'll comment shortly why do we keep sticking. I haven't said it yet, but why do we keep sticking to second order equations of motion? Now, how did we get to Galileans? We got to Galileans through people that were looking at higher dimensional realizations of gravity, such as DGP, Dvali-Gabadadze-Porrati theory, which is a 5-dimensional theory. There's a limit that is known as a decoupling limit, in which basically you decouple the different degrees of freedom in your metric. Some becomes irrelevant, and what remains relevant are the energies in which you're taking this limit, which are the energies relevant for cosmological perturbation, is the longitudinal mode of your graviton. So it's a scalar degree of freedom. By looking at this decoupling limit of DGP, it's a very complicated and technical procedure, and you need to know a lot about DGP theories. So there's a wonderful paper by Nicolis and collaborators. But anyhow, by looking at this scalar field that was basically emerging as the relevant degree of freedom in the low energy limit of DGP, and looking at it on a Minkowski background, it's a key aspect, they realized that this scalar was obeying nice symmetries that it had inherited from the Poincaré invariance in the higher dimensions. This symmetry was very simple. It was such that the theory was invariant under a shift and the so-called Galilean symmetry. So a shift of the field and a constant shift in the gradient of the field. And they realized that if you require a scalar field to obey this symmetry, so forget how you got to this scalar field. You require this scalar field to obey this symmetry, and you don't want the equations of motion to be higher than second order, then you will end up with a finite number of terms that you can write in your Lagrangians as functions of this field and its derivatives. They can be higher derivatives than usual, but they have to come in a very key, particular combination, such that overall your equations of motion remain second order. Now, they did this exercise similarly to what Lovelock did in general dimensions. And it turns out that for given d dimensions, there are d+1 terms, Galilean terms, that you can write such that your field enjoys this symmetry, shift and Galilean, and your equations of motion are not higher than second order. Those are the starting point for Galileans. Then, of course, they said, okay, we do not live in Minkowski. Let us go to Course space-time. And what happens is that if you want to stick to second order equations of motion, you have to inevitably non-minimally couple your scalar degree of freedom to gravity. That allows you, I'll show you the resulting action, that allows you to keep the equations of motion second order. In doing that, though, you lose the invariance under Galilean symmetry. We still call them Galileans. We call them generalized Galileans. They have this nice property that you can add a finite number of terms. That's a typical separation. Each of these will only contribute, will have second order equations of motion. So that's why they can combine in a very particular way. And you do not obey Galilean symmetry anymore. You have this non-minimally coupling popping up here and there. And not only notice we were used to have a non-minimal coupling in Brans-Dicke, depending only on phi. Now this non-minimal coupling can depend only on also on x, which is the kinetic term of your scalar field. Okay, so people got excited about these Galileans, also because they were encompassing most of the models that had been so far proposed for cosmic acceleration. You have F of R, you have quintessence, sorry, here. Well, there's no potential term in this case, because otherwise we lose the shift symmetry. But you can go to the more generalized case in which you give up also shift symmetry. But here you have your kinetic term. If you make it to be just a linear function of x, you can have quintessence. And then if you go here, you can have Brans-Dicke and F of R. And then you go to more complicated theories where you have higher derivative couplings. And that's going beyond the models that we are familiar with, but it happens to be exactly the sort of low energy limit of massive gravity and higher dimensional theories of gravity. So it's a very nice action, because just with four free functions of your scalar and the kinetic term of the scalar, you encompass basically all the models that I show in that branch, in the jungle of models that I show at the beginning. And the nicer thing is that at some point, people realized that these were nothing new. It was just Hordensky gravity. So generalized Galilean, this action is exactly equivalent to the action that Hordensky had written in 1974, just with a different language, but that was it. So just for the sake of completeness, and I'm not going to go through the details, but you can open up this paper, which is now highly cited, from 1974 by Hordensky, and you can find his procedure for identifying the most general action that you could have for a metric and the scalar field in 4 dimensions, such that your result in equations of motion are second order. And this is the starting point, scalar metric derivatives, scalar field derivatives. And then this is a very cumbersome way of writing the final Lagrangian. There's many things entering here, but what I should stress is the only arbitrary free function that are entering are these kappa 1, kappa 3, kappa 8, and kappa 9. These other things are fixed. FW, you can open the paper. They're fixed things. So your only freedom in there is in setting up this function. So it's equivalent to those G2, G3, G4, and G5 of the generalized Galilean. So Hordensky is famous. Then people start wondering, is this the most generic thing that we can do if we want to stick to second order equations of motion and introduce a scalar field? We could think of introducing vectors. They are not typically very useful, especially for the problem of cosmic acceleration, and they give you troubles with isotropy and homogeneity of the background. Tensors, yes, you can go introduce a second tensor, but let us stick to introducing a scalar degree of freedom, or at least effectively doing that. And why do we stick to second order equations of motion? We stick to second order equation of motion because of Ostrogradski's theorem, which is a theorem that tells you that as soon as you have a non-degenerate higher derivative Lagrangian, you will have, so out of which the equations of motion for your degree of freedom are higher than second order, you are inevitably waking up, introducing another degree of freedom, and it can be shown that this other degree of freedom, one of the two, will be a ghost, will have a negative kinetic term, a kinetic term with this negative sign in front. And that basically tells you that you run into instabilities of your theory. I will discuss this instability much more in the next days. So people really hold on to this Ostrogradski theorem, but there is a loophole. I mean, it says that you have non-degenerate higher derivative Lagrangian. Basically means having a positive definite kinetic matrix for your scalar degrees of freedom. What if you write a Lagrangian which has higher derivative in it? So apparently looks like an unhealthy Lagrangian that will have higher degrees of freedom, but it is degenerate. So basically it means that there are some constraints that between your among your degrees of freedom that you haven't noticed, and you can remove them and reduce to a Lagrangian that is effectively of the correct order and effectively propagates only one degree of freedom. People realize that indeed generalized Galilean or Hordesky are not exactly the most general Lagrangian that you can write if you want your result in equations of motion to be second order. There's a new sort of territory of which I'm not an expert at all, which is called DOST, that stands for degenerate higher order scalar tensor theories, or also known as beyond Hordesky. Now, when Hordesky heard about the fact that his theory was famous and people were working on it, he also found out that people were working on beyond Hordesky. So in the first paper with which he came back, he finished with a comment that was saying, nobody goes beyond Hordesky without me. So he was really taking it strongly. So there are some, I'm not an expert at all. There's a lot of literature. I'm going to give just a couple of references. This is by Glazes et al. And they proposed one of the first models that was going beyond Hordesky, but still sticking to one single scalar degree of freedom with second order equation of motion. That is known as GLPV for the initials of the people in the paper, Glazes, Langlois, Piazza and Vernizzi, I think. There's a very nice review by Kobayashi. I'm giving here the archive reference that discusses all Hordesky and beyond Hordesky theories and the status. Now, I want to mention also that another way in which this beyond Hordesky were discovered, rather than starting from a degenerate higher order derivative Lagrangian, was by performing what is known as a disformal transformation to a Hordesky theory. I will discuss conformal transformation tomorrow when talking about f of r. Conformal transformations are transformations that basically live invariant theories such as GBD. If you have a GBD model, generalized Brans-Dicke model, and you perform a conformal transformation, so you basically rescale your metric by a function of your scalar field, you will end up still with a generalized Brans-Dicke model. You do not introduce different terms such as higher derivatives or whatever, a non-trivial kinetic term. GBD and Hordesky itself is not invariant under this formal transformation. This formal transformation of this type, in which you rescale your metric not only by a function of the scalar field and its kinetic term, but you also introduce this function, explicit function of your scalar field. Some people notice the references are in here, but it was, I don't remember, I remember one of the authors, it's Miguel Zumalacárregui, I don't remember the other. They found out that if you perform this formal transformation on some Hordesky model, you can end up going beyond Hordesky, but still not activating Gauss. Now, that's as much as I can say about beyond Hordesky. It's a very new territory, and it looks like there are some very peculiar, interesting features from the cosmological point of view. So there are some papers, a couple of papers that have appeared that are studying cosmological perturbations and signatures on large-scale structure and cosmic microwave background. But it's a very new thing. Now, before I go to the more observational side, I want to finish with one slide about massive gravity. I'm not an expert at all of massive gravity. If you want to read more about massive gravity, there are wonderful papers by Claudia de Ram. She is the expert. Lavinia Heisenberg, and also Kurt Interbrinker. He has a beautiful review on massive gravity. So it's a very vast territory, and it's a very tricky exercise to give mass to your graviton. Writing a theory for a massive spin-2 field is not too difficult. The first attempt goes back to Fierz and Pauli in 1939. But then if you want to start coupling this degree of freedom to other particles, and that's what you should do if your spin-2 is mediating gravity, then things get very complicated. You run very easily into instabilities. It's very difficult to identify a consistent theory of massive gravity that does not develop Gauss, for instance, instabilities. And so I really don't know much. I know I always look at the sort of effective low energy limit of massive gravity, where what I'm left with is the longitudinal mode, so a scalar field. The modern idea about behind massive gravity is that of linking the mass of the graviton to the horizon scale. The mass of the graviton is protected by a symmetry. In the limit in which the mass of your graviton goes to 0, you restore gauge invariance. And typically we say that if there is a symmetry behind the 0 limit of your parameter, then it is technically natural. It is protected from quantum corrections. So that's nice to try to associate the cosmic acceleration to this technically natural parameter, the mass of the graviton. And even more interesting, it is when you promote the Newton constant that enters in your Einstein equation into what is known as a high-pass filter. You promote it to an operator that, in a way associated through the propagator to the mass of the graviton, filters out certain energy contributions. And in particular, you can make it work in such a way that it's a filter that decouples from the gravitational point of view vacuum energy. That's the idea behind the gravitation, which is born basically into a massive gravity or higher dimensional context for gravity. And again, I'm not going to, first, I'm not an expert. Second, it would take a whole lecture probably to go into the details of that. But it's the idea is I promote my Newton constant to an operator that filters out some energies and instead let pass some others. And I associate that, I act in such a way that the characteristic length scale, mass scales of this filter is associated to the mass of the graviton, because I do that working with the propagator of the graviton. And that's a very nice, that's to my knowledge, basically the only model that try to solve simultaneously cosmic acceleration, explaining it in a dynamical way, and also the smallness of vacuum energy. Because basically it decouples the question of what is vacuum energy from a particle point of view, quantum field theory, and what is the vacuum energy that we measure gravitationally. We degravitate vacuum energy, so it is still big from the quantum field theory point of view, but we don't observe its effect because of this filter. It's a very nice idea. It's not easy to implement it, and typically it is born in the realm of massive gravity and higher dimensions. Now, it's all nice, but there are many things you need to be careful about when you modify gravity. And I want to mention a couple. I already sort of hinted at those. One is local test. So gravity has been tested very well in the solar system. It's extremely successful around compact objects and so on. So while you are playing, trying to source, to explain the dynamics of the universe with a modified theory of gravity, you have to make sure that you don't screw up on local scales. And so typically, I've argued that typically whatever you do, you end up with at least one extra degree of scalar degree of freedom, which is non-minimally coupled, so it mediates an extra force, which we call fifth force, between your matter particles. You want this fifth force to be hidden in local systems, in high-density regions. And that can be done. I don't think I'll have time today. I'll go through the details tomorrow. That can be done through so-called screening mechanisms. The first beautiful paper introducing screening mechanisms was this one by Justin Curry and Amanda Weltman. I'll show you a concrete examples of how screening mechanism works. But that's one thing that you have to make sure. Your theory has to have a working screening mechanism in there. And I have already mentioned from time to time ghosts. In one of the next lectures, I will spend more time in describing exactly what I mean by instabilities, what I mean by ghosts, and there's other types of instabilities. But really, from the practical point of view of studying cosmological perturbations, it means that you will have some exponentially growing modes that gives you an unstable theory, and you want to avoid that. You want to avoid that, so you want to make sure that your degrees of freedom are healthy. And that, I'll argue, that is a very powerful way of ruling out models. Many models effectively introduce unhealthy degrees of freedom. And then the other obvious thing is that now we have observed gravitational waves. So as Stephen Hawking said, after straining our eyes, it is now time to strain our ears. So now we can also listen to the sound of gravitational waves. And that opens not only the era of gravitational wave astronomy, but also that one of gravitational wave cosmology. And there's why am I mentioning this in a lecture on modified gravity? After the first detection of gravitational waves from binary black holes, there was the one from binary neutron stars, and that came with an electromagnetic counterpart that was picked up. And that allowed to localize quite well the source of the gravitational waves and to do a lot of nice physics with it. You see the comparison with the localization of the source of the gravitational waves before there was any electromagnetic counterpart, and now with the electromagnetic counterpart. Of course, now that also Virgo is on, so LIGO, 2 interferometers from LIGO, 1 from Virgo, localization becomes better already only at the level of interferometers. But if you have the electromagnetic counterpart, it's pretty wonderful. And you can do a lot of physics, and in particular of interest to us is looking at the speed of propagation of these gravitational waves in the cosmological background. And that's the equations. It's a very simple equation where you have the speed of sound of gravitational waves, and by looking at the delay, time delay between the arrival of the electromagnetic counterpart and that of gravitational waves, which was tiny, which was small, especially tiny given the difference, the distance that the waves had to travel, they could put a wonderful bound, very stringent bound on the speed of gravity, which has to be basically equal to the speed of light. Now we are talking about gravitational waves coming from very low redshift. So it's up to your taste whether you want to take that as an absolute constraint on the speed of gravity, or whether you want to take that as a constraint on the speed of gravity today, and then face problems of fine-tuning. But anyhow, so let us say CT squared has to be equal to 1. Fine, it's probably you expected this. There were already some bounds on it, but that's the reaction of the modified gravity community. There was panic. For a few weeks, there was panic. The day after the paper about the combined detection of electromagnetic counterpart and gravitational wave came out, 3 papers, 2 of which with the same title, exact same title, then they changed it, came out saying what are the consequences for dark energy models. So it seems like on one side we were playing about modifying gravity, introducing scalar degrees of freedom to try to source cosmic acceleration, and we completely forgot that if you modify your theory of gravity, especially if you do it at the level of the action, you modify possibly also the equation for your tensor modes, not surprisingly. And many of these models we were playing with actually would modify the speed of propagation of gravity. So there was panic because it seemed that in 20 years in which we are playing with models of modified gravity and we have these large missions that will go out, one measurement from LIGO killed it all. It's not exactly like that, but yet it's wonderful complementary constraints and things that we have learned from there. So all the models that I've shown, if you look at their effect on the propagation for tensors, they might, some of them, for instance, FOVR, might modify the friction term in the equation. Some others, typical of Galileans, modify the speed of propagation. And there are models that do both. Now, the constraint on the speed of propagation impacts directly whatever terms of your theory comes in here. For these, you cannot use the speed of propagation, but you can use very other nice measurements, which is comparing the luminosity distance that you infer from the waveform of your gravitational waves with the luminosity distance that you infer from the electromagnetic counterpart. Whenever your theory has a non-minimal coupling, so introduces a term here, it will give a discrepancy between the luminosity distance that you infer from the waveform and the luminosity distance that you infer from the electromagnetic counterpart. So that's interesting. It's also a possible problem that can contaminate your inference of H0, for instance, from standard sirens. But that's an aside. What I wanted to focus on now is the speed of propagation. So it comes, you can get a modified speed of propagation whenever your theory has non-trivial kinetic terms. So you need to go beyond generalized Brans-Dicke. You need to go in the characteristic realm of Galileans, what characterizes Galileans. And of course, if you want CT squared to equal to 1, that's very obvious. You need alpha t to be equal to 0. But if you look at it in terms of the generalized Galilean action that I showed, it implies this constraint. These are the 3 papers that I mentioned. They all made it into a PRL issue that was basically dedicated to this. And so there is a constraint which basically tells you that if you do not want the fact that CT squared is equal to 1, if you do not want to achieve that in a way that depends on your background, but you want it to be independent from your background, basically you have separate constraint for what G5 derivative of G5 with respect to X, of G5 with respect to 5, etc., have to be. So you can take out different limits, and in simple terms, what it means is that you kill all things that are known as quartic and quintic Galileans, so the more complicated bits of the action, those that have non-trivial kinetic terms, and basically you are left with generalized Brans-Dicke, roughly speaking. There's a caveat, so I'm mentioning here these papers that are very famous by now. There's more works. In particular, if you're interested in this, you should follow up on papers by Paolo Creminelli and his students. He has a very other nice papers about other type of constraints, also from radiation loss. But what I want to mention is another paper by Claudia de Ram and John Melville, which we typically refer to as the rainbow paper, because there's a rainbow argument in there. But they make the subtle point that most of these theories, generalized Galileans, are sort of effective field theories. For your scalar degree of freedom, we use them in an energy range characteristic of our cosmological perturbations. And the limit placed through these gravitational waves comes from gravitational waves that have a frequency, so a characteristic you're looking at things at an energy scale, which is outside the limit of validity of these effective theories. So there might be an issue, and you might hope, for instance, of having your effective field theory to have some, to go towards a UV completion that eventually makes your CT square equal to 1 at the higher energies that have been picked up by LIGO. So there is a caveat. And in that sense, LISA, the space interferometer, which will be able to probe a vaster range of frequencies, might settle the issue. And then there's also the issue of at which redshift you have measured this. But to say, it was a very nice wake-up call. That's how I like to see it, because it made us realize that complementarity of different probes is crucial, especially if you do things such as modifying gravity. You cannot modify it on one side and forget completely about what happens on the other side. If you open one of those PRL papers, in particular the one by Miguel Zumacarregui and Esquiaga, you will find a nice table of which models survive the CT square equal 1 and which fail it. Some people say that it's an unfair table because it gives equal weight, equal volume to the green and the red. And we can argue which one has more volume from the theoretical point of view. But anyhow, so kinetic gravity braiding survives. General relativity, of course, survives. Quintessence, K-essence, and some sub-cases of a couple of theories that I mentioned. But the higher order Galileans are ruled out. Things that I haven't mentioned, known as fabulous 4 theories, are ruled out. And so it's really nice. It's really nice. OK, if you're still awake, for the next 20 minutes, I'm going to go more towards observational cosmology. And so what do we mean by cosmological test of gravity? So this whole exercise of modifying gravity, introducing quintessence or whatever, started sort of in combination with the observation of cosmic acceleration. So originally, people focused a lot on background expansion history. But then, of course, there comes the realization that there's more out there. We are observing more. We are looking at the clustering. So we will have, especially with the next generation of missions that is starting in a few years, we will have highly accurate measurements of clustering. And so we have to be able to confront our theories with that as well. And then also, there's also a realization of the fact that since when you go beyond GR plus cosmological constant, what you do is you introduce new degrees of freedom, so you have higher dynamics. Typically, you are able, and I show it with a FOVAR, to reproduce any expansion history. You can play with your degrees of freedom. Then we can argue how much fine-tuning you need of the parameters of your theory. But typically, whatever expansion history you give me, I can construct. I'll show it exactly the calculations, how it works for a FOVAR. I can build a model that gives me that expansion history. Also, lambda CDM. I can build a model that mimics lambda CDM. But it won't give the same dynamics for perturbations. You can perhaps reproduce exactly the same dynamic at the background level, but it won't give the same dynamics of perturbation. So cosmological perturbations and large-scale structures started to gain a lot of interest as the right testing bed for modified theories of gravity. This is a nice plot that I like to show that was made by Marco Raveri. He was a student of mine. Matteo Martinelli is a great senior postdoc in Leiden, now going to Madrid. And this is Gombo Zhao and Wang here. They have a code, Cosmic Fish, which is a code for forecast based on Fisher matrix forecast. And it can predict a lot of constraining power for many different probes, but also for many different theories. So here, what they're showing with this plot, you go in time here, so you go from COBE, WMAP, Planck, and into the future. And on the vertical axis, you have the bits of information. It's a way of quantifying in a very technical way. It's quantifying how much information you will gain about a model, given a probe. And here we are focusing on beyond lambda CDM, because technically speaking, also massive neutrinos, although it's a well-established thing, technically speaking, it's a beyond lambda CDM. And looking at some modified expansion history, some Lorentz breaking theories of gravity or Java gravity, etc. It's looking at how much information each of the different probes will give you about this model. And the main point I want to make is in comparing this, which was the past, with this that was the future. And you see here, all models are kind of, we are not learning much. We are really, what we have done so far is measuring exquisitely well the parameters, constraining exquisitely well the parameters of lambda CDM. But now we are opening the we have a prism that will open up our life, our different models, and we will have enough different type of measurements with enough accuracy to start disentangling and really probing many different models. And it's bits of information. It's something done with Kullback. I never remember. It's a very complicated thing, statistical way of measuring how much information. So it's a sort of units of information gain. If you look at the reference, it's too high statistics for me. But if you look at the reference, you find exactly how it's defined. And so this is just names of different surveys that will contribute to that. And you see I'm talking about, well, I don't think Lisa is in here, but I'm talking about gravitational waves on one side, clustering, weak lensing here and here, and then you have also sort of looking at the clustering with 21 centimeter. And you have also extremely large telescopes, are very interesting objects. I was quite ignorant about those, but there's very interesting things that you can do. And one thing that is interesting for modified gravity, or dark energy in general, is strong lensing time delay. It's looking at the time delay of light reaching you through different paths because of a source that is behind something that is a strong lens. So it's creating multiple images of your source, and if you have a variable source like a quasars, so that you can pick up a feature in time, you can measure the time delays of these light paths, and that's a very nice and complementary probe of your expansion history. It's setting a very competitive constraint of H0, but it can also give you interesting probes of gravity. Okay, so let me set the stage for the next lectures. And so let me go to the perturbed universe. Let us go beyond the expansion history. And most of the times, I'm going to work in Newtonian gauge. I'm focusing, as you can see here, on the scalar perturbations of the metric. I have mentioned gravitational waves, so I will eventually get in the final lectures. Also, I will get to the tensorial modes of your metric. But I want to start talking about large-scale structure, gravitational lensing. So all I need to worry about is the scalar perturbations to the metric, those the coupled to matter. And if I do it in Newtonian gauge, in particular in conformal Newtonian gauge, besides having the scale factor that gives the dynamics of the background, so it's something that I pick up when I do standard candles, baryon acoustic oscillation peaks, etc. I have the perturbations now, these two functions of time and scale. And this one entering the time component of my metric is the one that enters the geodesics for non-relativistic particles. So it's the one that we can probe when we look at things such as peculiar velocities of galaxies and the growth of structure. But then there's the combination, the conformal invariant combination, known also as Veil potential, phi plus psi, which enters into the geodesics of relativistic particles. And that's something that you probe when you look at weak lensing, or you look, for instance, on the integrated Saxoff effect of on the cosmic microwave background. So back again, more specifically, psi, you can think of it from the cosmological point of view as the analogous of looking at the orbits of planets on solar system. And we typically call that the Newtonian potential. Well, that's a video, but it's not really interesting. And the conformal combination, phi plus psi, I call it conformal because that combination is invariant under conformal transformation of your metric. So if you rescale your metric by a function of a scalar degree, of a scalar field, phi plus psi in the new frame will be the same. I will get to the details of that tomorrow. But this is relevant for massless particles. So when you look at weak lensing, at integrated Saxoff effect in the cosmic microwave background, and so on, you are probing the lensing potential. And it's basically analogous to things such as light deflection and time delay tests of general relativity that were done in solar system. Yeah, that's another way of saying why are we focusing on this function. So we have this the universe, and it's the space-time is described by this metric, and then we have several things out there making up our energy budget, and there's interaction. All of them, probably all of them, are of course coupled to the gravity, to the metric, but there can be also some interactions. Some are relevant at early times and then disappear. That's when you have the baryon acoustic oscillation imprinted. And some are possible or maybe are not there. It depends on whether your dark energy exists and whether it is minimally or non minimally coupled. But so the idea is that we have this cosmic drama where metric and matter are players, and they are all interconnected. So we have a set of equations, those that I have already shown, that are the Einstein equation that tells you how space-time is interconnected with your energy momentum tensor, but there's also the so-called Boltzmann equations, those that tell you how the different species evolve. You can do it with statistical mechanics, have a distribution function for your species, and the term on the right-hand side that takes into account possible interactions. At the end of the day, and this is what gives you the Boltzmann hierarchy of equation in your Einstein-Boltzmann solvers, for instance. At the end of the day, for structure formation, we mostly care about cold dark matter, which is non-interacting, pressureless. So these equations are very simple, and I will never really go into the details of Boltzmann hierarchy. Now, to justify what I will show in the next lectures, so we have matter. We know more or less what is out there. We postulate something for dark energy, for dark matter. We have our metric. We have our equations. We do the expansion history. We look at the perturbations. In particular, we look at linear regime when perturbations around the background are small. And we have this linearized set of Einstein-Boltzmann equations, but it's a very complicated set of equations. And there's very little. I mean, there's something that you can learn, but if you really want to have predictions with the accuracy and the extension of the observables that are out there, you need to use numerics. And the numerics in this case, as long as you stick to linear regime, are the so-called Einstein-Boltzmann solver. They are such that if you have a theory and you have some initial conditions and you know your content, you can evolve from early times up to today, stopping at any time that you want to get a plot like this, and predict what is the clustering of matter, so matter power spectrum, what is the CMB power spectrum, and so on. So why am I mentioning this? Because what we want to be able to do, besides playing with theory and modify theories of gravity, is to make predictions, accurate predictions, in such a way that upcoming observables will help us discriminate among the models. So it's already cumbersome to do it with a proper accuracy for lambda CDM. It is very complicated to do it for all those models. And whenever I will talk about ways of testing these models with cosmological observables, I will also spend some time mentioning the Einstein-Boltzmann solvers that you can use to do that. They are generalization of CAMB, or the alternative one, more recent, that is CLASS. I mostly work with CAMB. So the alternatives I'm most familiar with are things such as EFT-CAMB. But of course, there's equivalent codes in the CLASS sector. And indeed, we went to an excruciating process of code validation, because of course you want your code to give proper predictions at the necessary accuracy that you need for the upcoming data. And so we spent almost a year comparing these different Einstein-Boltzmann solvers. The biggest one are EFT-CAMB, and last lecture will be about this effective field theory of dark energy. So EFT-CAMB is an implementation of effective field theory of dark energy in CAMB. High class is similar, but it stands for Hordesky. But you will see the similarity between Hordesky and EFT of dark energy. So these are the two main codes, and you can do a lot of sub-cases in there. And for each of, besides being compared with each other, we have also for each of the sub-cases compared them with some model-specific codes that are out there. It was a terrible exercise with a lot of fighting, and but we converge. I don't have the reference, but there's a paper out there. So, can you keep awake for 5 more minutes? Yeah? Okay. So let me finish with the dense regions and going to nonlinear. And I'll jump to highly nonlinear. So far I've been doing basically I've talked about phi and psi, and I'll go more in details, but I'll do linear perturbation theory. You might have heard from Marcos going beyond that, starting to go into the quasi-linear and nonlinear. I make a jump and I go in a highly dense regions, which means highly nonlinear scenarios. And that's where the so-called screening mechanisms become important. Why do we call them like that? And why am I using a chameleon? Chameleon was the name used by Justin Curry and Amanda Weltman when they work out the first such screening mechanism. And of course, because of the camouflaging properties of chameleons, so something that adapts to the environment. That's the whole idea behind screening mechanism. You want something, a scalar degree of freedom, which adapts to the environment. And so if you are on large cosmological scales, it is light enough to source your cosmic acceleration with its dynamics. But as you go, a very light scalar field would mean a very long range force. When you go instead, fifth force, when you go in local systems, highly dense regions such as those of the solar system, you want this scalar field, for instance, to become very massive. That's one option, such as there is an exponential suppression of the fifth force that is mediating. It's a Yukawa type force. So that's the chameleon. Now, there's a couple of more mechanisms. In describing it, I mentioned the mass. So chameleon was the first such mechanism that was studied. And it is realized by having the mass of your scalar degree of freedom depending on the local density of matter. That's characteristic of FOVR. So I will show you exactly how it works for FOVR. But that's the whole idea. You have a Yukawa type force, so you have a term that is exponentially proportional to the mass of your scalar field. And if you make your scalar field becoming very massive in high density regions, there you go, you kill the fifth force. There's a couple of other things that you can do. So remember that big jungle of models. If you look at them in terms of how they can screen in local density, in local environments, there's really sort of three ways. So that's a nice way of sort of creating big classes of model. The one is symmetron, and it happens when the VEV, vacuum energy value, of your scalar field depends on the local density. And the coupling of your scalar field to matter is proportional to this VEV. So what you achieve is that your VEV goes to 0 in high dense regions. You sort of restore a symmetry. And then there's the one Weinstein, which is very different from these two. These two are very similar from the phenomenology point of view. Weinstein is very different, and it is related to the derivative terms of your scalar field. And it's such that you basically effectively decouple your scalar field by making its derivatives becoming very high in high density regions. Now, that can be summarized in looking at the equations that you can have for a scalar field and the things that you can make depend on your density here through the background value of the scalar field. So you can have a mass, you can have the coupling through the VEV, or you can have basically derivative terms either through the speed of sound or the overall term in front of your kinetic term, depending on your density. Let me briefly sketch how the chameleon is achieved. I told you it is characteristic of FOVR and in general, generalized Brans-Dicke theories. So theories in which you have a standard kinetic term, but you have no minimally coupled scalar field. Here you don't see any no minimal coupling, right? If you, for a moment, you don't look at this the matter part, this is pure quintessence. You have Ricci scalar, and then you have a standard kinetic term and the potential term for the scalar field. In reality, I have done something that I will explain. Was it already shaking or? Okay, it's time to finish. I have done something that I will explain tomorrow, but it's, I have hidden my scalar field here through a conformal transformation, okay? So it's not that the no minimal coupling now appears through the fact that the scalar field affects the geodesics of matter. It's just another way of looking at this generalized Brans-Dicke theory. But you see that if you now vary this action with respect to the scalar field, you obtain the equation of motion, the standard one, the D'Alembertian, the derivative of the potential, plus something that depends on this, which is basically the trace of the energy momentum tensor. So it's the density of your matter. And so it is, and it's horrible now, it doesn't show. I was lazy in changing colors. So you can imagine a system of axes here, scalar field, effective potential, and you can imagine of having a runaway type of sort of bare potential, the original one for the scalar field, typical of slowly rolling quintessence. And then you have a contribution that you don't see. There should be two contributions here, also in white, which is this bit coming from the energy, the coupling to the matter, something that is exponential in the scalar field and proportional to the energy density. Now, the overall potential of your scalar field is a combination of these two, so it has this shape. And depending on whether your rho is big or small, this effective potential opens or becomes narrower. And that means that the mass associated to the excitations around the vacuum is basically bigger or small, depending on the narrowness of your potential. So overall, you achieve, and I think I'll stop here and I'll go through the calculations tomorrow. So I'll stop with this plot that you can see. And so that's the whole idea. You achieve by having the matter, in particular the trace, that's a key part, the trace of the energy momentum tensor, so radiation does not enter here. You have only non-relativistic particles contributing here. For sure, you have your cold dark matter. Whenever you are in highly dense regions, these things narrows, becomes closer. The mass, the effective mass of your scalar field becomes very high. And then as you go away from the dense regions toward cosmological background, it opens up. And so I'll show you tomorrow the calculations. What you effectively achieve is that the scalar field goes from being very massive to light, far away from your source. You need the theory to have some characteristics. You need the source that you want to screen to have some characteristics, and I'll show you tomorrow which ones, in order for this screening mechanism to be efficient. And I think I'll stop here for today.
Questions for Alessandra?
I found it very strange when you said the speed of gravitational waves today is the speed of light. Could you tell us more about that?
You mean you find it surprising that it has to be the speed of light, or just today?
Both. That it's variable and that it's today.
Well, I mean, that it has to be the speed of light, there were already some indications. We had already a very stringent, I think, lower bound, right? And then with LIGO, we got the upper bound more stringent. So it's not so surprising if you have a Lorentz invariant theory of gravity with a massless graviton. It's also surprising that you expect to have a speed of the waves to be that of speed of light. What is very unlikely is that you achieve a scenario in which, in a natural way, your speed is equal to 1 today, but can be whatever at earlier times. It's similar to the problem, the problem of cosmic acceleration and this energy density that you need to associate to cosmic acceleration to be very small as we measure it today. You can achieve that dynamically with some scalar degrees of freedom that goes into this very slow, slowly rolling regime. But typically in order to do that, you need some fine-tuning of your theory, unless you can build up good tracker solutions. Then whatever initial state you start from, they will eventually go in there. And it's very complicated. I mean, it can be done. People are working on it, of building some tracking solutions for your modified theories of gravity in such a way that naturally at late times you go in the regime in which CT square is equal to 1. But it's not trivial at all. Yeah.
I remember we had a journal club just after these results on the 3 papers, and there was a string theorist in the room who said, "Why would you think the speed of gravitational waves should be different from the speed of light to start with?"
Yeah. That I think was my reaction, but I mean,
it was a part of the community, and we didn't think of it.
We didn't really, we thought we were playing in a completely different regime, and we never really, speed, if somebody asks you, you're like, speed of gravity is probably equal to the speed of light, and you're like, oh, wait a minute. So, yeah.
Some more questions for Alessandra?
lunchtime.
You mentioned the screening mechanism just a couple slides ago, but I couldn't understand exactly what it does, the screening.
Okay, so you mean this slide or more in general is what screening is?
I mean, more in general.
Yeah, so this is the point. Basically, whatever you do when you modify gravity or you play with dark energy, look at it as introducing typically at least one new scalar degree of freedom, which, unless there are strong symmetry arguments, is coupled to matter. And that means that it mediates there's an extra force between your matter particles. So besides having your usual, for instance, if you look at Newtonian gravity, besides having your usual Newtonian potential, going like 1 over r, you now will have a contribution going like, okay, a Yukawa type of contribution for the interaction between your matter particles, which has it can be a long range or whatever range force, depending on the mass of your scalar field that is mediating it. And we haven't seen it, because whatever we measure in high-density regions is very consistent with GR or the Newtonian limit of it. So this has to be completely, basically zero whenever you go in high-dense regions. So you need to screen it. That's where screening mechanism, where the word comes from. You need to screen whatever extra force your scalar field gives you. You need to screen that. You need to kill it. And there's different ways, different mechanisms by which you can achieve that. And the simplest, the first one that people could think of, was making this mass being density dependent. So when you go in high dense regions, that mass is very high, and that term is exponentially suppressed, and you will not see any extra force. Okay, does that answer?
So in low density environments,
in low density environment, in principle, your scalar field becomes, that's the cosmological sort of environment. I'll show you exactly tomorrow the solution for the scalar field. But in low density environment, you want to see it. You want to have a light, typically you want to have a light scalar field, because that would, then its dynamics would become important exactly at the characteristic length scale that, of cosmic acceleration, your horizon scale. So there is this sort of interplay between wanting a light scalar degree of freedom on cosmological scales and a very heavy one, if you have to have an extra one, or a decoupled one. And heavy is not the only solution. You can decouple it in another way, or in high dense regions. But I'll go through all the details of this tomorrow. It might become clearer.
Wait, Felipe. Sorry. Because we're recording.
Sorry, I don't know how off topic is my question, but I heard some authors arguing about the breaking of screening inside stars, and could you explain us a little bit about this?
Yeah, I think I'll try to address a little bit that tomorrow, because I'll have a part on the screening mechanism. It's a new, so I'll show you that the screening mechanism actually seems to be a very successful and well under control mechanism just around our below spherically symmetric cow, okay? And that's more or less as much as we have solved about it. And so around the homogeneous, spherically symmetric, isolated sources, you start changing your symmetry. You start having a density gradient in your source. So we don't know what happens. And yeah, it can break. And in particular, the screening mechanism characteristic of those degenerate higher order scalar tensor theories has that peculiar feature. Yeah.
More questions? Yes.
In your next slide, I think you showed to us, next one. No, next one, I'm sorry. Yes, this one. So in order to bring the action to this form, you have to perform this conformal transformation. So this somehow gives you a clue, the screening mechanism, for instance, this somehow gives you a clue of what of these metrics is the actual physical one. Because if, for instance, you have some violation of screening mechanisms, then you would also have, for instance, new physics or not.
That I'm not sure. Yes, I'll discuss the conformal transformation that you need to do, and if you know already about conformal transformation, it is in going between what is called the Jordan frame and the Einstein frame. So this is the Einstein frame, because that's where the action for gravity is the Einstein-Hilbert one. Now there has been a long debate about which one of the two frames is the physical one, and they're both, at least I think I can safely say that they're both physical frames. You just have to be very careful, because conformal transformation is a sort of rescaling of your units. So you have to just be very careful in properly formulating what your observables are. Once you do that, both frames should be equivalent. Now, I'm not sure I understood your question about the breaking of the symmetry of the screening. Maybe tomorrow, once we go through the screening, you can ask again, or later. Yeah.
Okay, so I don't see any hands, so let's thank Alessandra again. And we resume at 2 p.m.